All right, so for our second day graphing polynomials, we're going to need a few more factoring tools in our tool belt. So to graph things that are in standard form, we're going to need to be able to find the zeros by factoring. So there's a couple factoring formulas that we'll need. So as a quick reminder, always factor out greatest common factors first. So always look for greatest common factors first. And then if we happen to have something with two terms, we can see if it fits the pattern called the difference of two squares. So if we have two things that are perfect squares, commonly we might have something like, say in our first example here, x squared and 25. Those are both perfect squares, right? That's x times x, and that's 5 times 5. We consider those perfect squares. And there's subtraction between them. It's the difference of two squares. So this pattern always factors as a plus b times a minus b. So to figure out what our a value is, to follow our pattern here, we just need to figure out what times itself twice would make x squared, and what times itself twice would make 25. And essentially, it's like taking the square root of those. So this would be x, and this would be 5. And we'd use those as the a and b values. So we can think of that as our a value, and that is our b value. And then we're just going to follow this pattern. A plus b times a minus b. X plus 5 times x minus 5. And that's it. X squared minus 25 factors out as x plus 5 times x minus 5. Okay, let's try the next one. 4 and x squared are both perfect squares, and we have subtraction between them. So once again, we can fit our pattern here. This is x times itself twice, and this is 2 times itself twice. And that's the values we're going to use for a and b. So again, we're factoring as a plus b, x plus 2, times a minus b, x minus 2. X plus 2, x minus 2. Okay, now our next one gets a little trickier. 81 is a perfect square. That's 9 times 9. 4 I know is a perfect square, and so is x squared. So we can actually still write that term as something times itself twice. So 2x times 2x, right? 2 times 2 would give me 4. X times x would give me x squared. 2x times itself twice is 4x squared. And of course, 9 times 9 is 81. So for a, we're going to put in 2x. That's an a. And for 9, we're going to put in for b. So a plus b, 2x plus 9, times a minus b, 2x minus 9. And those are our two factors from 4x squared minus 81. Okay, last one. You might say 18 is not a perfect square, and you're right, and neither is 50. But x squared is, and there's subtraction. So remember what we talked about in the beginning. Look for a greatest common factor. So one thing I noticed is they're both divisible by 2. So what if we factor a 2 out first? Well, dividing each by 2 would give me 25x squared minus 9. And so inside of here, our remaining factors is a difference of squares. Right? This would be 5x squared, and this would be 3 squared. So he's using green there, huh? There we go. So we'll call this a and b. So we're going to get 5x plus 3, 5x minus 3. And don't forget, we still need the factor we took out in the beginning, which was 2. That's still one of our factors. So 2 times 5x plus 3 and 5x minus 3. So sometimes taking out that greatest common factor first, we can still make it fit our pattern. Now be careful though, we do not use a factoring pattern for the sum of squares. So if it's not subtraction between them, then we would not use this pattern. Okay. Next up, we have what's called factoring by grouping. This is the other new tool in our toolkit. So we're going to begin by multiplying these two things together. So if we were to multiply them, 2x squared times x is 2x to the third. 2x squared times 3 would make 6x squared. Okay, we've distributed the 2x. 5 times x is 5x, and 5 times 3 is 15. Okay, so what we're going to be given when we have this is the 4 terms. We're going to figure out how would we factor this back into these 2 terms. Okay, in fact, here is that exact polynomial. So here it is, nicely typed up, but the same answer we got by multiplying those. So here's how factoring by grouping works. We're going to group these into 2 groups, the first 2 and the last 2. And we're going to take out the greatest common factor from each group. Okay, so in my first group, well, the numbers are both divisible by 2, so we can take a 2 out. And they each have at least an x squared. So we're going to be able to take a 2 and an x squared out. And what that would leave me with, inside of our parentheses, 2x cubed divided by 2x squared. The 2's would cancel, and I'd be left with 1x, or x to the first power. 6x squared divided by our 2x squared. Well, the x squareds would cancel, and we'd be left with plus 3. All right, now here's what has to be true if grouping works. When we take a greatest common factor out of here, and it could be a 1, it could be a -1 sometimes. So sometimes it's just the number 1 or -1. But if we can take a greatest common factor, what's left in the parentheses has to be the same as x plus 3. Has to match. So what can I take out of this second pair? Well, they're both divisible by 5. So if I take out a positive 5, so write that as plus 5. 5x divided by 5, yep, would leave me with x. And dividing this by 5, we'd be left with positive 3. And this is what we needed to be true. We needed what was in the parentheses to match. Okay, and if you notice, x plus 3 is one of our factors. So be careful that x plus 3, the matching set of parentheses, is actually just one of our 2 factors. Okay, I guess I should write that in black. There we go. And on the outside here, the 2x squared and the plus 5, if you notice, is our other factor. So the common factors we took out become our other factor, 2x squared plus 5. And these would be our 2 factors, right, as we saw from the beginning, of that 4-term polynomial. Okay, let's try another example of this. So here, again, we're going to first look for any greatest common factor. I should have looked for that in the previous one, but there was not a greatest common factor. So greatest common factor of everything, no. Okay, but it does have 4 terms, so let's try our new method of grouping. So we're going to group first 2 and last 2. From this first group, 3 and 2 don't have a common factor, but I can take out at least an x squared. So let's take out x squared. Okay, so we would take out or divide out an x squared from each of these. This would leave me with a 3 and an x. And this last one here, the x squareds cancel, minus 2. 3x minus 2. Okay, so remember, when I take something out of this pair, what has to match or remain in the parentheses has to match 3x minus 2. Well, I think 9 goes into both of these numbers. But if I were to take out positive 9, already just looking at that last term, that would be plus 2, and that doesn't match. So I think what we'll need to do to change the signs is take out a negative 9. And if I divide each of these by negative 9, that gives me positive 3x and negative 2. So this time taking out a negative number was able to make those signs match. And again, remember, we had to get these to match. And just like we noted from before, the matching set of parentheses is one of my factors. So 3x minus 2 is one of them. And the other factor out here is given by the common factors we took out, x squared minus 9. Okay, well, check that out. This factor is a difference of squares, right? If we follow our pattern that we learned earlier, we can actually break this down further. That's x times itself twice and 3 times itself twice. That's what we'd use in A and B. So this would factor as x plus 3 and x minus 3. So we've essentially broken that factor down further. And we still have the 3x minus 2 that we took out earlier. So we end up getting these 3 factors in the end by using grouping. Okay, let's do one more just for good measure here. First thing to look for, remember, greatest common factor. All of them have at least, so we need to factor out the x as our greatest common factor first, which would leave me x cubed plus 3x squared minus 5x minus 15, right? We've each got one less x. Now inside of there, we still have 4 terms. We're going to try grouping on this remaining factor in the parentheses. So we're going to group the first 2 and last 2 and take out a greatest common factor for each. So in this first group, I can take out an x squared. When I divide an x squared out of each of them, that would leave me with 1x in the top. And here my x squared's canceled, and we would get plus 3. So remember, if grouping works, and it does not always work, what's left in our parentheses over here has to match x plus 3. So what would I need to take out of these two to leave me with x plus 3? A negative 5. Divide each by a negative 5. That would give me positive x. Divide that by negative 5, we get positive 3. And so remember, our one matching set is one factor. So x plus 3 is one of our factors. The x squared minus 5 is another factor. And that is not a difference of squares, so that won't break down further. And don't forget the x we took out in the beginning. So this is as far as I can break all these down. 5 is not a perfect square, so we can't break down that as a perfect or a difference of squares this time. So this is as far as we can go. All right, so now we have some new tools in our toolkit, which we'll need to use for some of these. So if I want to graph something that's in standard form, we can first look at our largest degree here. So our directions say factor, find all zeros, use multiplicity, the y-intercept, and end behavior to sketch a graph. So let's first look at our leading term. Because the leading coefficient is positive, remember that means the right-hand side is going up. And because it's an odd degree, that means they go in opposite directions. The left-hand side is going down. Next up, we can try to factor this out to find our zeros, or in standard form, remember that the constant, which is 0 this time, is our y-intercept. So my y-intercept happens to be at 0, 0. So my graph will pass through the origin. There's at least one point on my graph. Okay, next up, let's factor this to find all of the zeros. So the first thing I notice in my 3 terms they gave us is there is a common factor of x. And if we divide that all of them, we'd get x squared plus 2x minus 3. And because we're finding the zeros, we replace y with 0. And inside of here, we can try an x factor. We have a quadratic. So we spent a whole chapter factoring these. So they need to multiply to negative 3, add up to positive 2. And our 2 factors here would be positive 3 and negative 1. So this does factor using x factor as x plus 3 and x minus 1. Okay, and if I set each of these equal to 0, we're going to get x equals 0. From this factor, we're going to get x equals negative 3. And from this factor, we're going to get x equals positive 1. So our zeros and their multiplicity, because they're all occur only one time, it's going to cross at all of those values. So at negative 3, which is furthest to the left, my multiplicity is 1, which means it's just going to cross. At 0, it's only repeated once, so we're also going to cross at 0. And at positive 1, it's only repeated one time, so it's also going to cross. So let's mark these. Negative 3, 0, we've already marked, and 1. Okay, so our y-intercept, our 3 zeros are on here. We're going to start the left from below. And we get to negative 3. Because my multiplicity was odd, we're just crossing. So eventually we need to curve back down to head back towards 0, my next x-intercept, which we're also crossing with that odd multiplicity. And then head back towards 1, where we're crossing once again. And there we go. I get my right side going up, left side going down. We're passing through all 3 of those zeros, and we have our y-intercept. Okay, so here's our next example. We're going to do the same thing. In this case, it is in standard form. And my constant, which is negative 81, is my y-intercept. So yeah, that's a little out of my graphing window this time, but we can list it. 0, negative 81. So, you know, way down that way off my graph. All right, but my leading term is here. Because the leading coefficient is positive, we know the right side is going up. And because it's an even degree, we know the tail ends go the same direction. So they're both going up in this case. Okay, let's now find some of our zeros, and we can do that by factoring. So we're going to set this equal to 0. I don't see any greatest common factor here, but we do have a difference of squares. So if we use that pattern, what times itself twice gets me x to the 4th? Well, x squared. Remember, a power raised to a power, you'd multiply your exponents, right? That even matches up. And of course, 9 times 9 is 81. So using those as our values of a and b, a plus b, a minus b, these are our factors we get from the difference of squares. But hold the phone, this is another difference of squares, x squared minus 9. So we can factor this further using our difference of squares pattern. This is x times itself twice and 3 times itself twice. Remember, the sum of squares does not break down further, but the difference of squares over here does factor as x plus 3, a plus b, and a minus bx minus 3. So over here, this stays x squared plus 9, and now we're going to set all of them equal to 0. Either x squared plus 9 equals 0, or x plus 3 equals 0, or x minus 3 equals 0. Minus 3 equals 0. So from these two, hopefully we'd get some easy solutions. We're going to get negative 3 from this. We're going to get positive 3 from this one. But we do have a little bit of work to do over here. To solve for x, I think we can solve with square roots. Subtract 9 over, and then square root both sides. However, and again, this is why we spent this whole chapter on quadratics, that does get the square off of my x, but I have to remember to put plus or minus, and then this becomes, well, square root of negative 1, we're going to have an I in our answer, and the square root of 9 is 3. This is plus or minus 3i. So we end up getting two imaginary solutions here. So my zeros and their multiplicity, so we get a zeros of negative 3 and positive 3, and then we get plus or minus 3i, which we don't actually even count. So we're not going to graph those. You don't graph imaginary numbers on our normal Cartesian coordinate plane here. But these each appear once, and they're going to cross. So let's go ahead and mark these things in. So I have negative 3. We've got positive 3. My y-intercept, you know, is way down that way somewhere. So let's see, I come in from above. At negative 3, we're just crossing. I guess if you want, you can make it look like it goes way down to negative 81 and then comes back up. And then at positive 3, we're also just crossing. And that's it. We don't graph imaginary solutions. That just means it only crosses twice out of the 4 possible times. And that's because 2 are real and 2 are imaginary. Okay, last one here. Let's see. Greatest common factor? I don't see one. But I guess before we get to the zeros, let's talk about our end behavior. My leading coefficient is positive, so once again, the right side is going up. And because it's an odd degree, they go in opposite directions. The left side's going down. So now let's find our zeros. Or actually, let's do the easy. My y-intercept. There we go. My y-intercept is at negative 18, which actually is in my graphing window. We can graph that point. It's right here. Negative 18 is my y-intercept. Now, sorry, let's go back and factor. Is there a greatest common factor among these? No. But it has 4 terms. Let's try our new grouping method. So if we group first 2 and last 2, from this first group, I can take out an x squared from each. And if I divide out an x squared from both, we'd be left with x, divide out x squared here, plus 2. Okay, so remember, if this works, when we take greatest common factor out of this pair, we have to have x plus 2 remaining in our parentheses. Down here, x. And let's factor out. In this case, we're going to need to take out a negative 9. Negative 9. And dividing each by negative 9, that would give me positive 1x and positive 2. And there we go. We were able to get them to match, which meant grouping worked. Remember that the x plus 2 is one of my two factors, and that the x squared minus 9 is the other. So x squared minus 9. However, oh dang it, look at this guy again. It's the same one we've seen. That is a difference of squares. So we can factor out with x and 3 as our a and b values. So x squared minus 9 factors as x plus 3 times x minus 3. It's that difference of squares pattern. And then we still have this factor x plus 2. So here are our, x plus 2. Here are our three factors. And if we set each equal to 0, nothing too tricky this time, we should get negative 3 from this factor, positive 3 from this factor, and negative 2 from that one. So if we make our list, my zeros and their multiplicity. None of them are repeated. Man, nothing's bouncing off in our examples this time. We'll do some more examples in class. So these are all repeated once. It's going to cross at all of these values. And so let's go ahead and sketch this in. We can mark our 3 points, negative 3, negative 2, and positive 3. And of course, my y-intercept we've already marked down there. So we see from my sketch here, I know we come in from the left, from below. I need to approach negative 3, and we're just passing through, right, at negative 3. Don't want to go too far, because I got to pass through at negative 2, which again, we're crossing. Come down and eventually try to make it look like I hit my y-intercept. This doesn't necessarily have to be the bottom point there. But I do need to come back up to positive 3, where it's just going to cross on through. And so there is a good rough sketch of my last graph. Okay, we'll do some more examples of this in class. We'll definitely have some where there's more bouncing off the x-axis than we currently have.